Hi, this is Adam Wise, application scientist at Andor in the US, and today I just want to show you quickly how to use our signal-to-noise calculator. So this is for generating signal-to-noise curves for different cameras under different illumination conditions, so different wavelengths, looking at illumination per pixel or per area, and it's just a general kind of sandbox to explore what some of the camera's parameters and specs do to the actual signal-to-noise ratio. So let's start by comparing a Xyla and a Ixon, so an CMOS and an EMCCD. So I'm going to delete this initial camera that pops up, or I could change it, but I'm just going to do that for fun to show you how to delete them. And I'm going to add two cameras. Then once these cameras are on here, I can configure them how I'd like to. I could manually enter the numbers here, or I can choose predefined cameras here. So let's pick an Ixon Life 897 and a Xyla 5.5. So you can see it's populated the dark current, read noise, excess noise factor, quantum efficiency, and pixel size with the relevant specs for that camera. And what are the results? How do we read this graph that we've gotten? Keep in mind we're at 500 nanometer wavelength and 1 second exposure time. So what this means that on the y-axis we have signal-to-noise ratio. This is higher. The higher this is, the better uniformly. We don't want low signal-to-noise ratio. And I'll talk about what those actually mean practically in a little bit. And then on the x-axis here we have photons per pixel. So all the way from 1 photon per pixel, which is, well, I mean, you could go lower, but you know, for aesthetic reasons it goes down to 1. That would be kind of the mean arrival rate. And then over here we have 1,000 photons per pixel, which, while not that high in the grand scheme of things, is for us kind of the strong signal regime. So what we're seeing here is that the Ixon has a strong advantage in the weak signal regime down towards the single photon counting area, that we would not want to use a Xyla if we could avoid it for single photon counting. Instead, we would like to use an EMCCD because it fundamentally has a nearly zero or less than 1 read noise. Why does the read noise matter? Well, you can actually play around with this. Let's add a custom camera here, and let's take these other guys out. And we can see that we have, well, let's start with an ideal camera. So I'm going to change this to ideal. What does ideal mean? It means that it's strictly shot noise limited. So that is to say the only noise source is the fundamental jitter in the arrival rate of the signal. So there's no extraneous noise, no dark current, no read noise. Excess noise factor of 1, that's as good as it gets. Quantum efficiency of 1, which is to say that every photon that comes in gets counted. And a pixel size of 25 microns, which doesn't matter too much here. But what happens if we start to add some read noise? So let's add another camera and we'll compare to the ideal. So we'll start with an ideal camera here, and let's make it, yeah, it's fine. So we'll start to bend it relative to the other one. So what happens when we add some read noise? Let's say 1. Well, we're bending away. Let's go to 2. Bending away here. So you can see, and ignore that ideal sensor, I misnamed it. Actually, I'll just do it. I'll do a new one. Why not? There we go. So now we know it's custom. So now you can see it's bending away from ideality at weak signals. Why is that? Because read noise always happens. It doesn't matter how many counts you get. You're always getting read noise. So at the very weak signals, that read noise is extremely dominant because it's always happening. As you go further and further out, that read noise remains the same quantity, but it becomes a very small part of the whole ecosystem of capturing of light capture in that camera. Here we're capturing 1,000 photons per pixel. A couple of electrons of read noise on top of that is not going to change much. So we're approaching the shot noise limit at strong signals. So let me bend that back a little bit, maybe a little bit less. What happens if I add dark noise? Let me add 1. That's going to bend it more or less in the same way as read noise. So you can see I'm creating kind of a curved line that gets a worse signal-to-noise ratio, or a more extreme drop in signal-to-noise ratio at weak counts. What happens if I change the quantum efficiency, which is to say I change the efficiency with which I collect light? So now say if I change that to 0.5, that means I have a 50% chance of collecting a photon that comes in through the camera. You can see I've shifted my whole line down, that now I'm even suffering a loss in the strong signal regime. Because to me here down on the red line, When I'm at 1,000 photons per pixel in reality, actually, I'm only capturing 500 photons. So I'm going to be at the signal to noise of an ideal camera for 500 photons. So it's just a fun way, well, for certain values of fun, of exploring kind of what these parameters do. Finally, let's do pixel size here. So let me change this to a 6 micron pixel. Nothing actually happens right now because we're viewing this, if you see these options up here, as photons per pixel. I can also change this as photons per 13 by 13 micron pixel. So this is kind of an area of whatever 13 squared is, 169, I'm going to say. Probably wrong. And you can see if I change this to photons per area, all of a sudden the smaller pixel gets punished quite a bit. The signal to noise ratio drops massively. So if I switch back and forth, you can see if I'm careful to manage my magnification to keep the same number of photons per pixel across two very different pixel size cameras, then things aren't so different. If I if I show this in terms of area, so photons per area, all of a sudden my 1/4 size pixel is going to pick up 1/4 as much light and suffer an extreme drop in signal to noise ratio. What does that correspond to in real situations? Well, this is if you're just swapping the cameras. So you have a microscope, you're sitting in front of a microscope with an image, and I look at camera number 1, I say, okay, looks cool, let me switch to camera number 2. I just pop the camera off, put another one on without changing anything about the optics or magnification. And I say, oh boy, this image looks much worse, but I haven't actually controlled for pixel size. So I'm spreading the same image over a greater number of pixels, and I'm slicing it up into finer pieces. So each individual piece has less signal inside of it. And then finally, let me throw 2 other cameras back on here. I'm just going to dump these, add 2 more. Let's try 2 cameras that have very different performance, say at a certain wavelength range. Let's try an Icon L DD versus a say like a Zyla 5.5. And you can see we have a BRDD sensor in here. We could also choose a BEX2 sensor. These are both deep depleted sensors, which is to say they have very strong near IR sensitivity. So you can see right now the Icon L, and let's keep this as photons per pixel to keep them comparable, because the Icon L has a 13.5 micron pixel, the Zyla has a 6.5, so it's about, the Icon L ones are about 4 times bigger in terms of area. Right now we're comfortably in the visible. What if we change this to 700? And what if we change this to 900? All of a sudden you can see the Icon L kind of pulling away. What if we went to 1 micron? I'm not sure if the Zyla has data. Oh, it does. That we're going to get quite a stronger preference. We're going to show that the Icon L is quite a bit more performant, if I can use that word, higher performance than the Zyla 5.5 in the near IR. Let's see what happens when we change the exposure time too. Let's go back to 500. Oops, 500. And you can see that they're comparable. But you might notice that the Icon L dark current is 3 to the minus 4, 3 times 10 to the minus 4 electrons per pixel per second, where the Zyla 5.5 is 0.1, so it's several orders of magnitude higher in terms of the number of dark counts per second. So let's change this from a slender 1 second to, let's make it 10 minutes. Now all of a sudden you're going to see that we have quite a bit of gap opening up here where the signal to noise ratio, especially at low counts, is going to be much preferred in the Icon L, and that's because we're generating a lot of dark current, very little dark current up here, and comparatively more dark current down here, so that's going to interfere with the measurement of our signal. So that's the general idea. I'm going to record another video quite quickly about visualizing signal to noise curves, and I'll show you how to use that. But for the moment, if you have any questions, send me an email at a.wise@andor.com or visit the Andor website for more information.